Each 22 minutes, a secretive flag punctures the hush of the universe, perplexing space experts who have been hearing it for an unimaginable 35 a long time. This flag can be a totally unused infinite marvel, or a message whose calculation and genuine meaning we have not, however, caught on. Where does this puzzling flag truly come from? Why is it so distinctive from all other sounds and signals in space? And have researchers at long last found a conceivable arrangement? Signals in space are really nothing bizarre, but this flag, which we've been accepting with surprising consistency for 35 a long time, is not at all like any other sound within the universe. Whereas most enormous signals tend to be arbitrary or short-lived, this flag is demonstrated to be curiously steady over a strikingly long period of time. Infinite signals can begin from an extent of galactic wonders, counting stars, systems, quasars, quasars. Pulsars are a course of especially quick pivoting neutron stars that transmit high-energy radiation. These pillars travel through space like beacon signals and sound, just like the standard ticking of exact clockwork. Signals from quasars or dynamic galactic cores are more like commotion, some of the time with sharp crests, or prolonged on the off chance that they start from slower, large-scale forms within the universe. Quick radio bursts, FIRBs, are brief and amazingly strongly signals that, as it were, final milliseconds, likely originating from gigantic radiation sources such as quasars or gamma. Ray bursts, FIRBs, as a rule, sound once or with a number of redundancies and after that rapidly drop noiseless. The flag that has captured the consideration of analysts for 35 a long time does not fit into any of these categories. Like an energetic, enormous metronome, it sends a secretive flag each 22 minutes. Each signal consists of person beats enduring between 30 seconds and 5 minutes. These beats continuously happen at interims of precisely 21 minutes and 58 seconds, and final around 6.5 minutes. In spite of the inconstancy of the person beats, this source appears bewildering solidness due to the precise interims between the signals and its coherence over 35, a long time. Whereas the recurrence would be steady with a pulsar. The bizarre length of the beats between signals and the consistency of the design over decades contradict the behavior of an ordinary pulsar, whose signals ordinarily happen at much shorter, more normal interims and at the next recurrence. Analysts were flabbergasted when they listened this flag for the primary time in 1988. It was clearly distinctive from the normal chaotic commotion of space and caused a minor sensation. When regularities like this are noticed, researchers quickly explore for all accessible explanations. Within the case of the flag, which has been given the title GPM 1839-10, starting energy driven to hypothesis almost extraterrestrials and the possibility of to begin with contact. In any case, there was no affirmation of such contact, and researchers battled to create sense of the flag. Radio signals regularly sound like specific, irregular, or intermittent designs, and this was genuine with this flag. All translating strategies known on soil were incapable to extricate any more profound meaning from the signal. While we cannot run the show out the plausibility that other species utilize totally distinctive frequencies and calculations to send messages into space, our claim messages sent through radio waves have never been replied. Insights propose there can be around 30 brilliantly civilizations within the smooth way alone. GPM 1839, 10 raised questions about who might respond to our signals. The first signal of this kind was sent from the Arecibo Observatory in 1974, and later attempts to contact extraterrestrials via radio signals developed into the Organization for the Search for Extraterrestrial Intelligence, SETI. SETI scientists listen for electromagnetic signals that may have been emitted by extraterrestrial civilizations. Since the 1960s, scientists have developed various methods and technologies to filter potential messages or signals from extraterrestrial intelligence from the vast noise of the universe. These algorithms, called technosignatures, usually differ significantly from natural signals due to repetition rates and certain frequency complexities. Some critics compare this search to looking for a needle in a haystack, given the vast size of the universe. The ability to capture signals from cosmic events thousands of light years away gives hope, but we can never know who is receiving these messages. It is possible that not all beings in the universe, if they exist, are friendly. Whereas the secret of the GPM 1839, 10 flag remains unsolved, it has demonstrated that most signals traveling over long separations in space are transmitted by magnetars, pulsars, or neutron stars. When Australian analysts found an exceedingly unconventional magnetar almost 15,000 light a long time from soil in 2022, they were at first confused. This neutron star pivots exceptionally gradually, either demonstrating it is exceptionally ancient or speaks to another inconsistency. Regularly, a magnetar turns at a few turns per moment, but this one had amplified its revolution rate to 22 minutes. It isn't, however, known why a magnetite changes its behavior in this way. Ordinarily, ancient magnetars with slow rotation rates now not send out signals. However, this one does, which is exceedingly bizarre. The analysts are 100 beyond any doubt that this flag and the magnetar they found are the same. The magnetar was found within the group of stars shield, exceptionally near to the star grouping Sagittarius. The long interims at which GPM 1839, 10 emanate signals are appeared to be abnormal. Another comparative flag, radiating each 18 minutes, was taken note around a year and a half sometime recently. This revelation, showing the wonder, may happen more regularly than already accepted. Magnetars are uncommon shapes of neutron stars prepared with an especially solid attractive field, approximately 2 quadrillion times more grounded than Earth's and 20 trillion times more grounded than a commonplace paperclip's attractive field. These attractive creatures emanate expansive spectra of X-rays and gamma beams, went with by noteworthy stellar shutters on their surface. Magnetars can create powers comparable to the capable primordial constraint that shaped our planet. Neutron stars frame when a star detonates into a supernova. What remains can be a dark gap and conventional neutron star, or uncommon shapes of pulsars or magnetars. Normally, magnetars are, as it were, dynamic for months or a number of a long time, but the reality that such in question has been transmitting signals for more than 35 a long time is exceedingly bizarre. Researchers presently need to consider the secretive protest in more detail and trust to gain more principal bits of knowledge into the nature of neutron stars. The question has been given the temporary classification of an ultra-long period magnetar. Space experts around the world are tuning into space with tremendous radio telescopes. Nearly no sound. Get away the analysts, or maybe the analysts, or maybe the computers that screen the telescope's perceptions. It is barely conceivable for a human ear to recognize and channel all the signals and clamor from the universe. So finely tuned programs handle this assignment. All-gotten signals experience shrewdly sifting and investigation. When a recurrence or flag is recorded that the computers do not recognize, an alert goes off instantly. At that point, the information is checked on by researchers. There are handfuls of these cautions each month, but most are mistakes. Signals from wonders that are very simple to clarify, or signals from sources of impedances on soil or from satellites. As it were, approximately a dozen signals per year start from already obscure corners of the universe or mystifying occasions. Worldwide groups of scientists try to decipher and interpret these frequencies. Indeed, rarer are signals that contain so-called technomarks, which run the show out characteristic wonders as sources. The foremost removed flag ever measured was as of late gotten by 2 analysts from Canada and India, Astronomers. The discovery of GPM 1839-10 and its potential link to an ultra-long period, magnetar opens up new avenues of research into the nature of these enigmatic celestial bodies. Magnetars are already considered rare and peculiar due to their immense magnetic fields and the extreme conditions they represent. However, finding one that defies typical behavior by emitting signals over such a prolonged period challenges our current understanding. This discovery could provide crucial insights into the life cycles and evolutionary processes of neutron stars, especially those with unusually slow rotation rates. Studying this magnetar in more detail may reveal unknown mechanisms that allow it to sustain its activity far longer than any other known magnetar. Additionally, the regularity and duration of the signal from GPM 1839-10 have sparked discussions about the possibility of other unknown or misunderstood cosmic phenomena. While the magnetar explanation is compelling, the precise intervals and sustained emission also raise questions about whether other, as yet unidentified processes might be at work. This could include novel interactions between magnetic fields and stellar material or entirely new categories of astrophysical objects. If similar signals are discovered elsewhere, it might indicate that ultra-long period magnetars are more common than currently believed, or that there are other cosmic structures capable of producing such emissions. Finally, the ongoing advancements in radio astronomy and signal processing technologies are crucial in detecting and analyzing these extraordinary phenomena. As telescopes like China's FAST and Australia's Murchison Wide Field Array become more sophisticated, they increase our ability to capture faint, distant signals with greater clarity and precision. Enhanced computational methods and machine learning algorithms also play a vital role in distinguishing meaningful signals from the vast background noise of the universe. As we refine these tools and techniques, we enhance our chances of uncovering new astrophysical mysteries, potentially leading to groundbreaking discoveries about the fundamental workings of our universe. The study of GPM 1839-10 is just one example of how modern astronomy continues to push the boundaries of our cosmic knowledge.